Hey everybody, welcome back to chapter 9. In this chapter, we're going to talk about concepts and generic knowledge. As I was preparing these PowerPoints for this presentation, I was struggling to remember how much I already told you about semantic knowledge versus how much I should repeat. And so I sort of took out the semantic knowledge part because I think it's too repetitive with my earlier lecture. So hopefully you remember back from, I think it was chapter 7 when we talked about, sources of knowledge or, sorry, not knowledge, memory stores. Um, this picture I've got here on the first cover is illustrating one aspect of concepts, which is, you have the concept of, um, animals, and we have a system for describing different kinds of animals. In this case, we've got a red fox, and we have the system that can tell you exactly what kind of animal a red fox is according to this classification system. This is one way that we manage generic knowledge. This is one way that we sort of normalize the understanding that we all have of these different things. I don't know about you, but I didn't take enough biology to really have domain, kingdom, phylum, class, all that stuff become second knowledge for me, like second nature. But some of you might be really familiar with that, so I thought I'd throw that in. I'm going to go ahead and give you our quick lecture outline. First, we're going to spend a little bit of time talking about concepts themselves and special cases of concepts like prototypes and exemplars. And then I'm going to spend a little bit of time talking about the associative network theories. That's not exactly something that's covered in our textbook, but I think it's really an important explanatory moment to sort of talk to you about how our different concepts might be organized in our semantic memory store. And then we'll talk about the typicality effect. We will kind of distinguish categories from concepts and also explain how they kind of work together. And then we'll wrap it up by putting it all together and make it hopefully clear why this is important, at least to a person who's studying cognitive psychology. All right, well, let's jump in. Okay, so let's start off by defining what a concept is. Concepts are defined as a mental grouping of details pertaining to an object or class of objects. So, first thing on the list is it's mental. It's something in your head. It's something, in your brain somehow, probably in your semantic memory store. So, you have this mental grouping of details that pertain to an object or to a class of objects. So it kind of sounds like an associative network, which we've talked a little bit about before in class. The idea that you may have, spreading activation and other things that we've talked about in class. When you activate one detail about a concept, it makes you think about other details about a concept. So concepts are these mental groupings of specific details that pertain to just a specific class or to a specific object. So here's a concept for you, the concept of mom. Now, there are probably a lot of things that are being activated in your brain as you're thinking of the concept of mom. There might be behaviors that are associated with a person who is a mom. There might be sort of ideas that they might hold, ways that they might look, all these kinds of disparate, right? Those are very different things, behaviors and appearance and ideals. And these are all very disparate things that might all contribute to this overarching, class of objects that have offspring that they care for, right? Called a mom. So a concept would be like thinking of the concept of mom. A prototype would be your best example of a concept. Now, the best example in a prototype is not a single example. It's oftentimes like a conglomeration of lots of different examples that you've come in contact with, and you've sort of gleaned from that experience that a good example of this concept would have these characteristics. It's possible that our brains go through life, doing a kind of statistical analysis of the frequencies of different kinds of behaviors and things that might be associated with our concepts, right? All the different moms that you've met in life, in real life or in the media or whatever, you may have been distilling down those consistencies, the things at least that you're noticing that are consistently present for the people who you would call mom, right? So you may be doing some kind of comparison and not even know it, as you're trying to understand what constitutes a member of this category, right? That kind of distillation and lumping them all together is what we mean by a prototype. It's not usually an example. Like I've got, since I used the Brady Bunch house as my memory castle along, several chapters ago, I thought I might as well use the mom from the Brady Bunch as like a prototypical mom. When you say something is a prototypical case for that category, what you're saying is that they have enough of the characteristics that a typical member of that category should have. Right now, I don't know whether the Brady Bunch mom actually has enough of the categories to qualify in your mind for a prototypical mom. I don't know. All of our experiences are different. And so we may have different minimum qualifications for the prototypical example of the category mom or the concept mom, right? So that's fair. We're all allowed to sort of have our own definitions, and that's true for any concept. What it means to be a pet, right? Some people may have a vastly different definition of what it means to be a pet, what characteristics would be present in something that we would call a pet versus what somebody else might define. And that's the important thing to remember about prototypes, is that they are based on our own personal experience, and so we all have our own personal prototypes. Now, there are some prototypes that we might agree on, to some extent, but we might have some objections and say, yeah, but that one's missing something that I think is really important. Something that I would say is critical to that concept is missing, but I can see why we might call that a prototype. I'll let you have that one. That's close enough. We don't have to agree on prototypes. We just have to know what our own prototypes are, right? We have them. It's what gets kind of called forth when we think of something, a concept. An exemplar would be a specific example of the category or concept. So my mom would be an exemplar of the concept mom. Um, on the level of prototype, I might, rather than saying Carol Brady is a prototypical mom, I might say TV moms, right? Like maybe I'd have a prototype where I think moms should behave like TV moms behave. And maybe I just have like this generic hodgepodge of Carol Brady and Marion Cunningham from Happy Days and Roseanne Barr, or what was her last name? Connor, Roseanne Connor from the Roseanne Show. And then maybe I'm trying to think of another more modern sitcom mom. I'm doing only sitcom moms, I think you might have noticed. I can't think of any good ones. Like I don't know the name of the mom on an old sitcom called from the 90s called what about Jim, or I can't remember the name of the show very well, so I don't know the moms. So I could lump them all together and call them TV moms. And maybe I have this generic concept of what it means to be a TV mom, right? I lump them all together and now I have this prototype that is TV moms. And that my prototype of TV mom might vary substantially from what it means to be a mom, like an actual mom. I hope they vary because actual moms don't have writers. I'm just going to say they have to think of all that stuff on their own. So I'm going to say that. So you have this generic concept, and then you may have a prototype based on your brain's amalgamation of all the different examples that you've met and what you've pulled out as good examples, qualities that make it clear that this person belongs to the concept. That's probably your prototype. And then an exemplar would be thinking of a specific case, right? Thinking of a specific one and thinking that they're a good example. Like if I'm going to say that is my mom and I think she's a good typical mom, like that would be a good example of a mom. I might be holding her up as an exemplar. Now, we might again argue about whether my mom's an example of typical mom, or some maybe she's got the extra things or is lacking things from what you would expect from an exemplar of the category of mom. um, but that's the basic premise of these three things. So you can kind of see we go from the most general, which is the concept, to prototypes where there's like these expectations and maybe a little bit of a statistical component to like what is most commonly associated with a good example of that concept. And then we have finally like a very specific example that we're going to point to and say this would be an example. The exemplar would be something that we point to and say this is an example of what I mean when I say that concept. So you could go through this exercise with like the concept of dog, and then maybe your prototypical dog. What characteristics does a prototypical dog have, right? And then finally, you might think, well, my dog is a good example of a the category dog. He'd be a good example, so he's an exemplar. I'm thinking of all the dogs I personally know don't really match my prototype of a dog. I've occasionally seen a dog that kind of looks like my prototype. Um, my prototype of a dog is like kind of Snoopy from the Charlie Brown strip, newspaper strip. So kind of like Snoopy, but Snoopy's a beagle supposedly. So I think my prototype is actually a little bit bigger. I think that, but I like that in my prototype. I think of a prototypical dog should have ears that are about the size that Snoopy's ears are. I think that Snoopy's tail is a good representation of what a dog's tail should be in my mind. And I'm not saying it because that's what my dogs have looked like. I don't know why I think this is a prototype. And I think it needs to be a little bit bigger. Like I think that a dog in my prototype would be, I don't know, knee high, something like that. Whereas I think, Snoopy is probably more like mid calf, probably tall. So I feel like, oh, it needs to be a little bit bigger than, right? So I've got like these things that Snoopy's a good example, but he does lack some aspects of what I think my prototypical dog looks like. And none of them look like my dog. The closest dog I've ever had to my prototype was my last dog that I had, and he was a German short hair. And so, if you know a German short hair, he kind of, if they hadn't cropped his tail, which I didn't ask them to, he came like that. He might have looked even more like my prototype. He was the right size. I think his ears were a little too long for my prototype, but they were in the range. You know what I mean? So that's the thing about concepts versus prototypes versus exemplars, right? Like you're getting more specific as you go down the list. Okay, well, hopefully that's made that really clear. I want to hop into the associative network theory discussion. We're going to spend a significant amount of time talking about this. So here's a attempt someone made to try and draw an associative network. You can tell what the theme is on this associative network. So the idea here is that there are associations between concepts, right? These are theoretical links between details that are present in any concept. So in this network that's being illustrated over here, the big overriding concept is liquor. And then you have all these different associated components, right? Like details that can be linked to the concept of liquor and then also to each other sometimes. Some of them are linked back and forth to each other. And so that's what we're talking about in the associative network theory is that you've got this net of details that are linked to each other. And that these links can be varying strengths, right? Like the link between liquor and alcohol might be a stronger link than, let's say, the link between maybe liquor and sweet. Like maybe that's a weaker link. Or liquor and store might have a really hard or really strong association because liquor store is a common phrase, and so you might have a really good strong association between that and maybe a weaker association between liquor and strong or something like that. So not all of those, just because these lines are drawn doesn't mean that they're all of the same impact. They don't all have the same strength. So I'm going to take us back into the olden days of yore when, forever psychologists have been attempting to teach machines language. Yeah, they've gotten really good now. If you've played with Chat GPT, you know they're getting pretty good now. Siri and Google Assistant do a really good job of natural language. You can speak to them. Even my Amazon Fire Stick does a good job of hearing what I'm saying and attempting to produce a response that's appropriate for what I asked. So language is not always about them talking back. It's about understanding what's being said to them also, and then producing some kind of response that's appropriate. Well, Quillian back in 1968 attempted to teach a machine language, to try to teach a computer language, and what what they found is that you can teach a computer to draw inferences, to make assumptions about what must be true, and that kind of shows that these associations between details can be solidified. These associations between the details within a concept can be solidified so that you're having, the computer talk about or think about a particular detail associated with another particular detail often enough that it starts to draw an inference that these things are maybe synonymous, or that these things are really sort of important or quintessentially, a component of this concept. So the computer can start to make inferences. Sorry about my weird vertical line there. So one thing that Quillian noticed is that it seems like the computer was showing a hierarchical conceptual organization. Um, Based on how long it took the computer to answer different kinds of questions, Quillian came to the conclusion that there's like an overarching animal concept, a bird concept, like a subset of animal would be bird, and then of course you could go down this line and do fish. And then you could keep going down bird and land at canary or ostrich or whatever. And what Quillian suggested is that for economy, and in an old-timey computer, computers had to be economical in their storage because they didn't have much storage capacity. So for economy, you would store the general principles at the highest level you possibly could and assume that they infer that they must apply to anything below. So an animal has skin, can move around, it eats, it breathes. At the next level, the bird, we're going to assume a bird has skin, can move around, it eats and breathes, and in addition has wings, can fly, and has feathers. Right. And then now we go down a little bit lower. And so we know that a canary has skin and blah, blah, and has wings and blah, blah, and also can sing and is yellow. Right. So we only store at the different levels those details that are unique to that level. And everything above it applies to the stuff below it. So that makes a lot of sense, right? We have a little problem. This picture actually came directly out of Quillian's research, and you'll see a version of it in your textbook too. We have a little problem. What if instead of canary and ostrich, well, actually, ostrich is a good example because you have can fly at the bird level, and ostriches can't fly. I was thinking, what if we put penguin in there because they can't fly and they don't technically have wings. I guess, they kind of have wings, but they swim with them. They're more like fins. So it's like violating two rules to be an ostrich, sorry, a penguin. So sometimes when you have a case that violates the upper rule, you have to actually spend a little bit of extra effort to store that detail down here, right? Like an ostrich has all those characteristics, but we have to negate the flying part. Can't fly. But we have the other parts, right? Has wings, has feathers. So this hierarchical conceptual organization assumes that you're going to store as much detail as you can at what's called the superordinate level. And it's going to apply to everything below. At the subordinate level, you'll apply all the details that apply below that, right? And then at the coordinate level, you're going to have the information that's unique to that member, that makes it different from the other members at the coordinate level. So that's the premise on the teachable language comprehender, is that we have economy of storage, and we're only going to store information where, in one place whenever we can. And that our brain does like the computer and infers that, well, if it's a subordinate of animal, then it must have all the characteristics that an animal has. If it's a coordinate of bird, it must be that it has all the characteristics of bird, unless we note to ourselves, this is a special case. This one breaks the rules. Just memorize this about an ostrich, or just remember that about a penguin that violates the rules. All right. So what we're basically showing is cognitive economy. Through this teachable language comprehender, Quillian was able to show that, probably like computers, we organize information as economically as we can, so that it takes as little cognitive effort as possible to store the information. Okay, so here's the kinds of questions that you would ask a human. Does a canary have skin? And what you find is that it takes the human longer to say, yes, a canary has skin, than, because they have to go hoppity hop bird. I don't see anything about skin here. Hoppity hop animal. Okay, I found at the superordinate level, yes, they all have skin, kind of thing. So it'll take longer to answer the question, does a canary have skin? I think I have another question here. Oh, I guess not. Than if we were to ask, can a canary sing? That's going to be a quicker response, right? If I have to go up to the subordinate level, or I have to go up to the superordinate level, there's actually a category size effect where we actually see it taking longer as you're hopping up those levels. Another assumption of this model is that all coordinates are equal. And so any question that you have to answer that is stored about the canary at the canary level would take you as long as any question that you would answer about the ostrich that could be answered at the coordinate level. So you should take the same amount of time to say that a canary can sing as you would take to say an ostrich can't fly, right? That we shouldn't see a difference in the time to process questions about coordinate level details. Where we would see a delay is if we have to hop up to the subordinate level, or we have to hop up to the superordinate level to answer the question. So this is basically what we see in humans, that when you ask them these questions, a canary is the fastest, right? A canary is a bird. A canary is an animal. We're seeing longer response times with each of those questions. A canary can sing, a canary can fly, a canary has skin. Each of those takes longer than these more direct, I'm just asking, is it a member of the subordinate category? And that takes less time than to identify that the case actually meets a specific criterion of that subordinate category. So this is taking a little bit longer because we're asking details about the subordinate category, whereas here we're just measuring the subordinate category. But look at how the pattern is pretty similar, right? As we're going up the levels, it's taking us longer. And we see that with humans on these kinds of prompts. We see it with teachable language comprehenders also. All right. Let's go ahead and stop here, and I want to talk about another associative network theory, which is the spreading activation model. So I will see you in the next video.